Hey there, science fans! Today we're diving into the fascinating world of adsorption. You see it every time you use a sticky note or see water droplets cling to a window. But what's really going on at the atomic level? Let's find out. Adsorption happens when molecules from one substance, like a gas or liquid, stick to the surface of another substance, which could be a solid or even a liquid. It's like these molecules are playing tag, but instead of running away, they decide to hold hands and hang out together. Think of it like this. Imagine tiny little balls of energy representing molecules bouncing around. When they get close to a surface, they sometimes get trapped, sticking to the surface like a magnet. This sticking process is what we call adsorption. Adsorption plays a vital role in many natural processes and industrial applications. From purifying water to developing new medicines, understanding adsorption can help us design better solutions for a cleaner and healthier world. Now you might be wondering, how do these molecules actually stick together? It all comes down to molecular interactions like tiny little handshakes between molecules. When molecules from different substances get close enough, they can start to feel each other's presence. These interactions can be attractive or repulsive, depending on the types of molecules involved. Think of it like trying to fit puzzle pieces together. Sometimes they fit, and sometimes they don't. When attractive forces are stronger than repulsive ones, the molecules want to stay close to each other, leading to adhesion. You know, like when you press two pieces of tape together and they stick? That's adhesion in action. These molecular handshakes are essential for adsorption because they allow molecules to stick to surfaces and form a thin film. Without them, the molecules would just bounce off each other like bumper cars and never really get together. But what creates these attractive forces between molecules? Well, it's all about the force, the surface force that is. These forces, also known as van der Waals forces, are weak attractions between molecules that arise from temporary fluctuations in electron distribution. Picture it like this. Imagine electrons are constantly buzzing around the nucleus of an atom. Sometimes these electrons bunch up on one side of the atom, creating a temporary dipole, a region with a slightly positive or negative charge. Now, when another molecule comes close, its electrons are also buzzing around, creating their own temporary dipoles. These temporary dipoles can then interact with each other, like tiny magnets attracting or repelling. These van der Waals forces might be weak individually, but when you add them all up over a large surface area, they can create a significant attractive force that holds molecules together. It's like the saying goes, many hands make light work. Section 4, the Goldilock Zone. Distance is key for adsorption. Here's the thing about these surface forces, they're pretty picky about distance. Think of it like the story of Goldilocks and the Three Bears. The distance between the adsorbate, the molecule being adsorbed, and the adsorbent, the surface, has to be just right. If the molecules are too far apart, the van der Waals forces are too weak to hold them together and they won't stick. It's like trying to hold hands with someone who's standing across the street. You just can't quite reach. On the other hand, if the molecules get too close, their electron clouds start to repel each other, like trying to force two magnets together with the same poles facing each other. So, for adsorption to occur, there's a sweet spot, a Goldilock zone, where the distance is just right for the van der Waals forces to work their magic. This distance is usually on the order of a few angstroms, which is about the size of an atom. Section 5, Adsorption in action, from water filters to your DNA. Adsorption is more than just a cool scientific phenomenon. It's a fundamental process that plays a vital role in countless natural and industrial applications. Take water purification, for example. Activated charcoal, a highly porous form of carbon, is often used in water filters because of its exceptional adsorption capabilities. The porous structure of activated charcoal provides a massive surface area for contaminants like chlorine, pesticides, and heavy metals to adsorb, removing them from the water and making it safe to drink. But that's not all. Adsorption is also essential in fields like medicine, where it's used in drug delivery systems to target specific areas of the body. It's even crucial for life itself, as adsorption plays a key role in how DNA molecules bind together. Section 6, wrapping it up, the essence of adsorption. So there you have it, the incredible world of adsorption. We've learned that it's all about molecules sticking to surfaces, thanks to those fascinating van der Waals forces. Remember, these forces might be weak individually, But when you combine them over a large surface area, they can create a powerful attraction that holds everything from water molecules to pollutants in place. Understanding adsorption is crucial for developing new technologies and solving important problems, from cleaning up our environment to advancing healthcare. So keep exploring, keep asking questions, and never stop learning about the amazing world of science.